Okay, we are going to continue on with our discussion of dense fluids and their properties. So in general, what we've talked about we can either use statistical mechanics to come up with, for example, configurations of the system. In this case, we did an example of a lattice fluid model using a mean field approximation for the energy. So the total number of configurations is equal to the partition function. Or we can use molecular dynamics or Monte Carlo simulation techniques to also get access to samplings of particle positions. Then if we combine this, we can get a collection of particle positions. Whereas this is going to be like the set of the position vectors for an n number of particles. Now in the case of molecular dynamics, we can get this as a function of time. In the case of Monte Carlo, we can get a sort of collection of this information. What we'll be talking about today is we'll then take this information and discuss how we can calculate the radial distribution function. We talked qualitatively, but today we're going to talk quantitatively of how we're actually going to calculate the radial distribution function given a set of atomic positions. And then we'll conclude today once we have access to the radial distribution function, we can then calculate the internal energy, the pressure, and a number of other thermodynamic properties that we need to calculate. So today's lecture is going to be filling in this part here. All right, so we've already talked about how we can generate positions. Now, how do we analyze them? So, the radial distribution function is mathematically defined as such. 1 over rho squared. Yes, and I'll explain what this all means here. Oops. These brackets you will commonly see in StatMech mathematics. These brackets mean that you will perform this calculation over all particles and all orientations of the system. So for example, in an MD simulation, we are going to get the position of all particles as some function of time. Which means that this integral, we are integrating over the entire volume of the system. We will perform this calculation for every single particle, particle 1, particle 2, particle 3, particle 4, particle 5, for each time step. Then we will repeat that for all the time steps in the system until we get to a convergent solution. Right? So we need to do this calculation sufficient times that we can actually get enough statistics that we can have accurate data. That's what these brackets mean. So when you see those in the code, that basically means repeat this a bunch of times for all particles, for all orientations in the system. In this case here, I've written the radial distribution function. Sorry, this is g of r, but this is a vector. This is three-dimensional, right? This is a 3D position vector, meaning that if I have, for example, a sheet of paper, right, it's asymmetric. That means that the structure above and below, in the case of the paper, is symmetric, but along the edges is not symmetric. If I have a ball, like argon, that is isotropic, meaning there is no orientation, in which case you don't necessarily need to do a full 3D representation of the structure. That makes sense. So R, this is going to be our angular dependent position vector. So for example, students in my research group, we will go to a neutron scattering facility, and we are more or less attempting to measure the radial distribution function. Now in a real fluid, right, if I have a glass of water and we shoot neutrons at it, those water molecules are tumbling and rolling and rotating around. What we're looking at is a time-averaged sampling of the configuration of the system. Those water molecules don't want to stay fixed in a particular position so I can get 3D structure. But what we do instead is we use some clever Monte Carlo simulation techniques to model this to give us access to the 3D structure. So when we report what the structure of a fluid is in our publications, we will look at it from a 3-dimensional perspective. For argon, it's 1-dimensional, not a big deal. R prime, this is just some displacement vector that gets integrated out. Displacement vector. And then lastly, actually not quite lastly, the density function. This is the collection of discrete points that represents where the particles are located. This is the Dirac delta function. So in the computer, or on paper if you are a glutton for punishment, the density, or this is the position of the system. This function is always equal to 0 unless R is equal to R of I. Everywhere else is equal to 0. So the Dirac delta function also has the property, let's see, right here. If you integrate from negative infinity to infinity of the Dirac delta function with respect to x, this is just equal to 1. It's just there such that it's convenient to use for these types of situations. Okay, so what the radial distribution function is trying to tell us. Basically, what does this mean? Right. What does this abstract mathematics tell us about what's actually going on in the system? So, what this is saying is that this function here is going to be equal to 0 unless there is a particle, in this case particle I, is located at the same position as your vector. Okay? So this is only going to be equal to 1 if, well, in this case it's actually equal to infinity, but we're integrating it out. This is only going to be finite, non-zero, if there's a particle at that position. This function is only going to be non-zero if there's a particle at the same position as R and another particle displaced by R prime. So what I mean by this, let's draw it out. This is our arbitrary origin. In this case here, R is equal to 0. This is in 2-dimensional space. This could be, for example, Rx, Ry, but imagine we could also do this in 3 dimensions. Now if I have a particle here where R is equal to Ri, that would be there. Actually, let me draw this a little bit differently. particle is here. In this case, R of I is equal to R. Then if I add in a second vector here going in some other arbitrary direction, I'll call this R prime. If there is a particle here, this corresponds to R plus R prime. The only time this function is not equal to 0 is if at some arbitrary position there is a particle and there's another particle some other distance away. And then we repeat this for all particles in all positions. But that's what this function here represents. Does that make reasonable sense a little bit?
I'm not sure what the point is, but it makes sense.
The point of all of this is such that when we have a box containing a collection of particles, what we care about is not the absolute position of what those particles, where those particles are at, because it doesn't matter, because they keep on tumbling and rotating. It's an all dynamic process. But what we do care about is relative to one particle, what is the probability that there is another particle a certain separation distance away? So this is just the tedious mathematics in order to get us to that concept. We care about the structure of the fluid relative to the positions of the individual particles. So when I do this in a simulation, I will define an arbitrary x equals 0, y equals 0, z equals 0. But I don't care where my particles are relative to that arbitrary reference. I only care where my particles are relative to the centers of all of the other individual particles. Because that is the environment that the fluid is going to feel. Does that sort of satisfy a little bit, at least qualitatively, why we're doing this all? Okay, so this function here is not particularly useful unless you are trying to solve it analytically, which can only be done with very simplified systems. So instead, we're going to simplify. Oh, one other quick note. This factor right here, the density is equal to N over V. So if we do the substitution here, this expression 1 over rho squared V is actually equal to 1 over rho N, if you just do the simple substitution. So what this is saying is that you're normalizing this integral with the bulk average density and the number of particles in the system. So you're going to repeat this calculation for all the particles in the system. So you're normalizing it by the number of particles, and you want to compare it relative to the density of the fluid. And that's why the radial distribution function always decays to 1. Right, so if you were to look at a radial distribution function, it'll be 0 in the excluded volume zone. You'll have your first solvation shell, your second solvation shell, and eventually it just decays to 1. And beyond that, your fluid is basically structureless. Right? You can't discern the long-range structure. Now, a crystal has long-range order. We'll have a radial distribution that looks something more like that, where you have a regular periodic array where there's always going to be a crystal at a certain separation distance. But as you get bigger and bigger and bigger, that'll eventually wash out as well. Okay, so we're going to simplify this because this expression here is convenient mathematically, but conceptually it's very abstract. So we're going to do a couple of steps. We're going to sub in that the density is equal to N over V, and we're also going to sub in that this rho function here is just a collection of discrete particle positions. we're going to replace the integral with a summation, because this here is not a continuous function, this is a discrete function, so there's no point in integrating it anymore. Now we're just going to add up all the different particle positions. 3, we are going to radially average the system, so we're going to convert the position vector into the magnitude of that vector, and we'll just call that R instead. So this is going to be the case for a randomly oriented fluid. This function here as a vector is only going to be important if you're looking at the 3D structure. But in this case, we're going to just look at it as a randomly oriented structure. Okay, so with these approximations, we can rewrite that expression as such. Okay, so let's decipher this really quickly. What we're going to do is we're going to start with particle 1. Okay, so I'll call this one particle 1. If there is another particle distance r away from particle 1, right? So let's say, for example, this is distance r. There's no particle in a spherical radius distance r. That means I'm not adding anything to my radial distribution function sort of tally. So I'm going to go from particle 1, then I'll say, okay, now what about this r? Nope, still no particles. Now at this r, aha, there's actually a particle. So that just adds up to 1. Right? So in this function, it's saying that there is nothing going on unless, for particle 1, I'm going to check every single r. This r, this r, this r, this r, this r, this r, this r. Oh, eventually we find a particle. I count that as 1. I keep on doing that until I check all the different r positions away from that particle, and I count up all the number of particles that are exactly r distance away from that vector. Then I repeat this process for particle 2. Then I repeat this process for particle 3, then for 4, then 5, then 6, and so on and so forth for thousands of times if you have a big simulation box. Then I repeat that process again for every single time step that I have access to, or every single configuration of the system. That's what these brackets mean. Then I'm going to normalize it based on the number of particles, orientational averaging, and the bulk density. That is practically speaking how we're going to do this. Now there's only one other step before we get to the actual computational implementation of this code. And that we're going to replace this Dirac delta function with the step function, doing a little clever arithmetic. But the problem here is in how we've written the g of r. For a real system with a finite number of particles, this r has infinitesimally small steps, meaning that we need an infinite sample size in order for us to get accurate statistics of the system. We're not going to have a smooth graph of the g of r because this r is infinitely thinly sliced. So instead, we're going to add in a resolution. Right? Because effectively you would have to take infinitely small step size. So in a practical implementation, we need to add in a resolution for our radial distribution function. How closely can we measure these sharp peaks? So if we do that, the implementation is that the radial distribution function is going to be a function of the separation distance between two molecules and the resolution that we're going to choose for our calculations. So if we do this, we will get a different looking function. So double summation I equals 1 to n, sum I equals not j, sorry, j equals not I. We're going to use the step function, and I'll walk us through this in just a moment again. This is the actual function that we will program into software to calculate the radial distribution function. All right, example time. This capital sigma function is the step function, so it's 1 for x greater than 0, and it is 0 for x less than 0. So what that means is that it looks like this. Nothing, nothing, nothing. As soon as you hit 0, it jumps up to 1. Now, practically, what this is saying is that if I have a box, see if I can draw this out well, and I have a particle here, I'm going to call this particle 1. I can then have some distance r away from my particle, and within there, I'm going to draw a spherical shell. We're then going to have some additional resolution called delta r, and within there, that is going to create a spherical ring around particle 1. Now, if we fill in particles, let's say this is particle 2, this is particle 3, this is particle 4, 5, and 6. So with this function here, this first term, this is for whether or not J is outside of the ring found by R. Okay? So let's take, for example, particle 3. Or let's do particle 6. This right here is R1, 6. That is the separation distance between your particle 1 and particle 6. That vector magnitude is greater than R, meaning that you're going to have a value here equal to 1. We've satisfied this first logic term there, saying that 6 is outside of the ring formed by R. Next, we have R plus delta R. This needs to be greater than the distance. And it is. R plus delta R is farther away from particle 1 than the R16 vector, the distance between particles 1 and 6. So since these two numbers are larger than this one, this is also going to be positive. So this term right here corresponds to whether or not J is less than outer ring. And if so, oops, it is equal to 1. So this logic programming here is basically kind of like a bunch of if statements. If particle 6 is farther away than R, okay. And if particle 6 is less than R plus delta R, okay, we're going to count it. So then how we calculate the radial distribution function again is we repeat this process for every particle every r for every time. So if I have 100 particles in 100 configurations and a resolution of let's say 1 angstrom in a 10 by 10 box, let's just say hypothetically. So I have a box where n is equal to 100. I have number of configurations is equal to, let's say, 100 different configurations I'm averaging over. And then let's say my delta R is equal to 1 angstrom, and my edge of the box here, I'll call it Z, is equal to, let's say, 10 angstroms. That means that the number of calculations is going to be 100 particles times by 100 time steps times by the number of times that I have to do this, times by, let's say, in this case here, it would be for every particle we have to repeat this calculation approximately 10 times. And that's just the number of pairs of comparisons. Then within each of those, we have to then execute logic statements where we're calculating the separation distance between all of these individual particles. So it adds up very, very quickly. Now for a real simulation, we will be doing this over thousands of particles, over thousands of time steps, with resolutions on the order of fractions of angstroms. Right, let's say 0.1 angstroms, 0.01 angstroms. So producing this information is non-trivial. But this is the only way to think about liquid structure. Because liquids randomly tumble, randomly orient, we don't care about their position other than the position of the particles relative to one another. So another way to think about it then is we're looking at the frequency that we would expect to find particles, right? So in a crystal, if I have a periodic lattice, in this case I'm drawing a simple cubic crystal structure, I don't care where this particle is. It doesn't matter to me. Molecules and atoms are so small, it doesn't matter where the particle is. The only thing that matters in determining the structure, the properties of the system is what is the frequency or the repeating nature of the crystal. If I know that every single particle, I have a certain probability of finding particles separated by distance L, a certain distance M, a certain distance N, that's all that I need to know. Because if I have a pairwise potential, I just need to know the number of particles, the number of neighbors separated by what distance. So I know a number of you folks, or at least I guess just maybe one of you here, is doing controls on. So when I'm doing something that doesn't depend on actual absolute, but depends on frequency, what do you think of? Open question for everyone. If I don't care about the positions, but I care about the frequency, what mathematical tool do I have access to analyze the system? Does anyone do sound analysis?
The Fourier transform?
Fourier transform. So this is why when we think about fluid structures as not about the absolute positions of the particles, but the relative positions of the particles according to some frequency of separation, that means that we can analyze fluid structures by looking at it in what we call reciprocal space or Fourier space. What is the frequency domain of the structure as opposed to what is the absolute positions of the system? And that's why there is a direct one-to-one analogy and comparison between the radial distribution function and the diffraction pattern. So what happens in diffraction is that we shoot a wave of a particular wavelength at our system. And the only thing that matters is the relative wavelength compared to the relative separation distances between the particles. And according to Bragg's law, which we'll discuss next week, according to Bragg's law, then that gives us access to the information of the relative probability that there are particles of a certain separation distance relative to the wavelength of that radiation. So when the wavelength of the radiation is approximately the same as the separation distances between the particles, you can create constructive and destructive interference, which is the foundation for Bragg's law. But the sort of philosophical concept behind this all is that because atoms are so small, it's useless for us to know what the absolute positions of them are. The only thing we care about is the relative positions of molecules relative to other molecules, because that controls what the energy of interactions of the system is. And that's ultimately what we care about. We want to know what is the potential energy of the system. Entropy is a little bit more complicated to get, but if we know the potential energy and we know the pressure, for example, then we can get access to all other thermodynamic properties, according to the Gibbs phase rule. If we know 2 macroscopic thermodynamic properties, we know everything we need to know about the system. And that's what we're going to do right now, is we're going to show what equations we can demonstrate where we can connect between our microscopic scale and our macroscopic scale. All right. So the first one is internal energy. We can write that the internal energy of the system is going to be the contribution from the internal energy of that particle as an ideal gas, plus what we call the configuration energy. So in the case of an ideal gas, this is going to be necessarily equal to 3/2 N kBT. Now in homework 7, which I will assign today, it'll be due, I think, next Thursday. So we'll have next week to go over it, and please do look at it so that we can go over the questions. This is going to be the killer right here. In all of StatMech, everything is per particle. So which means that a lot of you will crunch numbers on the homework, and you'll get results like times 10 to the minus 30, times 10 to the minus 60, times 10 to the plus 70. Because that usually you run into the situation where you go, okay, should I times by Avogadro's number or divide by Avogadro's number? And if you get that wrong, you have a factor of 10 to the 46 difference between your answers. So sometimes it can feel hopeless when you're doing StatMech calculations because you need to be really diligent about your units. Okay, so the internal energy of an ideal monatomic gas is given by here. So if we assume that the local configuration doesn't change the energy modes of that pure compound, then we can have the energy is the ideal gas energy plus the energy from configuration. And here we'll call this the configuration energy. Right, this is going to be the energy of all of the cohesive interactions of all the particles in the system. So we can write this then as U is equal to the internal energy of the ideal gas plus the configuration energy, which we will write as such. So conceptually, what we're saying is the radial distribution function contains within it the average density of the fluid given a certain separation distance away. So what this is saying basically is we're going to add up the average number of particles separated by some distance r multiplied by the potential energy of that separation distance. And if we do that from 0 separation distance to an infinite separation distance, then that tells us that we're adding up all of the total energy on average of all the particle-particle interactions. So let's do a really quick unit check. So N is dimensionless, but oftentimes when I do my unit analysis, I always put a little number sign in there, a little hashtag, to remind myself that it's like transitioning from numbers to moles, because it kind of keeps it consistent a little bit. The density is number per volume, so I'll write that as per cubic meter. The potential energy, parapotential, has units of joules. Now when you actually read stat mech literature, they'll probably have different units like ergs or EV or things like that, because single molecules have very, very, very small number of interactions, so they be small. G of R is dimensionless. R squared is meters squared. dr is meters. So we have the 3 on top, 3 on bottom, and we get the correct units of joules. Good. All of these complicated stat mech equations are just equations at their heart. Another relationship that we can derive from the radial distribution function is the number of molecules in solvation shells. So the number of particles separated some distance r from a reference particle is going to be equal to so that if I draw a reference particle some distance r away, this will tell me how many particles are within that shell. So if I have a fluid with really, really sharp peaks in the radial distribution function, right? So if I have a fluid with the sharp peaks like this versus a fluid with small peaks, that means that the fluid with the sharp peaks in the radial distribution function has many more molecules in the near locations surrounding any individual reference particle. And of course, this is all averaged over all particles, all configurations, all times. Okay. We've got a few more equations that are sort of the classic foundations of molecular simulations. We have the pressure equation. In which case the pressure of the system. We have our ideal gas contribution. Right, this is just the ideal gas law. It's written in a slightly different form. Right, rho is N over V, so this is pressure is equal to N kBT over V. That would be the standard form that we see from classical thermodynamics. Minus 2 pi And again, let's break down this equation really quickly. What we're saying here is that, again, we have the average structure of the fluid, and then the slope of the parapotential will give us a force. That's how we design molecular dynamics simulations. So whether or not your average density is in the region where the particles are attractive or repulsive, that is going to be a correction factor to the ideal gas law. Right, so if you recall, if we have a standard 612 Lennard-Jones parapotential, in this region here, we have attraction, and in this region here, we have repulsion. And that's going to be related to the slope of the parapotential. Whether or not two particles here are going to want to roll down or roll this way. So the slope of the parapotential is going to be the net force of attraction or force of repulsion as a correction term to the ideal gas law. So let's double check our units. Density squared gives us the number per meters cubed squared. Our pair potential is going to have units of joules per distance, which is going to be in meters. G of R is dimensionless. We have meters cubed times by meters. So let's see, how many do we have? We have, let's see, 1 over m to the 6th joules per meter, meters to the 4th. This is going to give us, let's see, 7 over 3. Is that, sorry, did I get this right? Let me see. Okay, so a joule is a meter cubed Pascal, right?
Yeah.
I think I got something wrong here. Hold on a second. Let me check. So this is 1 over meters to the 6 joules per meter. 4th. Hang on a second. Meters to the 6th, joules per meter, meters to the 4th. So this is going to give us, okay, so we have meters over 4, meters to the 7 times by meters cubed Pascal. Oh yeah, again.
Yeah.
7 over 7, this gives us units of pascals. Save myself an embarrassment. Okay.
And is the negative sign, you said that the force was the negative slope, right? Is that why there's a negative sign there?
I believe so, yes.
Okay.
Yeah, so in this case here, if in this region here, du dr is less than 0, so that means that we need to be, the molecules are on net pulling each other towards one another. So if that's the case, then this should be decreasing the pressure. So this here would be negative, so negative and negative, oh, let's use negative. If you didn't have this minus sign.
It's greater than 0 there.
Oh, okay.
Yeah.
Oh yeah, it's positive, sorry. So this is positive. So if that wasn't the case, then this would be contributing, oh no, that's right, yeah, it'd be negative pressure. Yeah, sorry, that's right. If we're in this region here, the slope is negative, meaning that the negative and negative would give us a positive, which would be then the fluid would be pushing against the wall harder than we would expect normally. Okay, lastly, is the compressibility equation. It gives us access to the pressure, but implicitly. But the advantage of this is you don't rely on a pair potential. You don't necessarily have to have a pair potential. If you have access to just the radial distribution function, you can then determine what the fluid pressure is going to be. But necessarily, you would have to repeat this at different densities. So let's say, for example, we were trying to calculate the effective pressure of our lattice model. We could use the compressibility equation, but we would have to apply our lattice model at different densities, and then we would have to do thermodynamic integration to give us access to the pressure of the system itself. But in many regards, this is a very commonly used equation in simulations to give us access to macroscopic properties. So, the reason why I spend so much time on fluids is because when it comes to property predictions, anything low density gas phase is relatively trivially handled by equations of state. Their deviation from ideal gas behavior just is not big enough that it's really a problem that we don't necessarily have a 100% accurate static model. Now, where things become really challenging is when we're dealing with high density fluids. When we're dealing with high density fluid, it's not like a crystal. We don't have access to what is the structure of the fluid at any given snapshot. That's not possible due to the Heisenberg uncertainty principle. We don't know where all the molecules are at any given point in time. And even if we did, they're all interchangeable, and in a picosecond, they would all be in different positions anyway. So the only way, really, that we've come up as sort of a scientific discipline of understanding how to think of fluids is through the time positionally averaged structure. What is the relative position of one molecule to the next? And the best way that we found to describe that is through the radial distribution function. This is also an asset because the radial distribution function is directly related to experimental measurements using scattering techniques. So one of the key questions I always like to ask people is, only recently, within maybe the past 10 to 15 years, have we developed really, really powerful analytical techniques. Non-contact AFM-STM, scanning tunneling microscopy. Only recently, maybe in 2000, I think, there was a science paper that was published that actually was able to visualize benzene when it was absorbed on a perfect crystal monolayer background. But before the year 2000, we knew what benzene looked like. How did we know that benzene looked like this, that ethane looked like this? How did we know that? Chemists back in the 1800s knew that benzene had the same number of carbons as hydrogens. They knew that carbon had anywhere between 1 and 4 chemical bonds, I guess, well, 2 to 4 chemical bonds. It has to be bonded to something. Right? They knew these things. So by deduction, they kind of thought this is what benzene looked like. But they could only do that for really, really simple compounds that they knew how to break down into the individual elements. But the real power for how we were able to determine what atoms looked like, how they organized, how bonds are formed, what are the structure of those bonds, is all from diffraction theory. So if you ever read any papers and you see anything that discusses scattering, it's discussed as like a monolith. It's its own discipline, because the foundation of all of chemistry is so critically dependent on the ability to know what these molecules look like. The only way that we were able to do that is through the radial distribution function, through the structure factor, using experiments. So what would be done is you would take benzene and you would crystallize it into a single crystal. You would take that frozen chunk of benzene. You would have to have it of a finite crystal size. You would shoot your radiation at it. You would measure the diffraction pattern coming off of it, and then you would rotate it. Rotate the crystal this way, rotate the crystal that way. And your diffraction pattern would change. Knowing how to understand and interpret the structure of the system in a full three-dimensional orientation gives us access to not only the intramolecular structure, but also the intermolecular structure. What is the crystallization structure of benzene? And I believe, in fact, benzene crystallizes in a herringbone structure. So the benzene molecules crystallize like this. Access to this information was only possible due to diffraction. The reasoning for that is atoms are extremely, extremely, extremely small. So small that there's no technique that can visualize them, because light is many of orders of magnitude bigger than molecules are. Visible light, rather. So with the discovery of X-rays and the identification that when you have radiation with a similar wavelength as the separation distance between particles, you get constructive and destructive interference. That's how the Braggs were able to derive Bragg's law and sort of absolutely explode the field of chemistry. Without that, it would basically be impossible to be able to know what the structures of all these different configurations and systems are. So it's a critical aspect of the history of science, and it's not necessarily something that we're going to directly be applying on the exams. Now, you will have to know how to apply these formulas for potentially an exam, but I'm not going to make you, calculate what a radial distribution function is. But I am going to try and make sure that the exam questions are worded such that you will have to know conceptually what it is, what's the information contained within it. But if nothing else, walking away with sort of a mental image of how we should think about fluid structures is one of the real cornerstones of what I want to accomplish in this class. Because it is sort of the backbone of all modern thermodynamic research. And every single one of your fields, I promise, you will be able to find some simulation that better describes or helps you describe the system that you're looking at, regardless of area. Simulation tools are so prolific now that you need to be well versed in the language and nomenclature of those particular disciplines. All right. Have a great holiday. Thank you all for submitting your papers to me for the project, and I'll see you on Monday.